start up in about 5 seconds. Welcome back, everybody. I hope you had a good weekend. Looks like a beautiful week is starting to form out there. I just wanted to look at the homework just real quick. We will have a review session on Wednesday, 5:30, if you can make it. I'll record them. Probably eventually I'll make them private, and I'll just hide them. But the link you have will always work. I'll be persistent. It just won't be advertised on the page of the thing, so I can do that. So if you want to have access to those in like 5 months to go, store the link. If you don't remember to do that, and I do, not publicly disclose them, you can always send me and say, hey, I really want to see how you did this problem. But anyway, that's a problem-solving session. You guys get to ask questions. I get to, spend lots of time talking about what my steps of my integrals are or whatever. So that can be useful for you. So hopefully you guys ask some questions on Slack and are able to attend. I just want to run through the questions real quick. So problem 1 is just working through the posterior predictive when you don't know what sigma is. So I put it on phi scale. I kind of get a 2-for-1 out of this problem. I first have you work through the posterior on phi given x. That's a good problem. You need to integrate out mu to do that. So it is that same integral that we just did. You might complete the square or figure out what completes the square and invert that thing. So just like we did before. So it'll be one of those e to the plus 1/2, whatever the mean, divided by its variance is. Mean squared divided by the variance. Same integral that I did last time, different context. So integrate over mu, you'll come up with that posterior distribution, phi given x. And then I want you to use that to figure out the posterior distribution on x tilde given x. So that has mu integrated out and phi. You could solve this problem just by doing a double integral, but we've already done one of the integrals. So we've already integrated over mu in this one. And so you know the problem, you know this. This is kind of where I'm aiming at. It's not the only way to do this problem, but we already know this in a normal problem. So what's this thing? These are going to be xi's, x1, to xn. Each of these things are distributed normally, mean mu, precision phi. So what is this thing right here?
Normal.
It's normal. Good. Which normal?
Mu.
Careful. You've integrated out mu. It's x1. So now we're there. One of these days, we'll get you to stop saying the thing that you've integrated out. It's obviously a plug. I think I maybe did it once in grad school too. So this is sigma squared over n. So I just flip over my sigma squared. I don't flip over the n. So we don't flip that whole thing upside down. But in terms of phi, it's that. So we know what this is right here. We've already solved it. We've already done one of our integrations. Once you come up with pi phi given x, I can just take this thing right here, whatever this is, I'll call it pi if you like. So this thing is normal, so to get this, if I have this and I've integrated out mu to get that thing, then all I have to do is just marginalize that out. So this is going to be equal to integral pi x tilde given all of my data that I've seen, condition on phi, pi phi, then our condition on x. It's not conditionally independent of it. X is what informs me. So you don't just integrate over the prior. You have to maintain the conditioning on x. And you're going to integrate between 0 and infinity. So first part of the problem, figure this out. You're going to integrate over mu so that you can get this thing right here. So you'll get the joint distribution of phi and mu, integrate over mu. All. Then take it and do this step. So keep track of everything very carefully. So I'm going to ask you to do stuff like this on the midterm. So it's not easy the first time you do it, but it eventually becomes easy once you do it a time or two. Okay, so I'll have you do that. Basically, it just changes everything to t-distributions. Totally not surprising because we're integrating over something that looks like a gamma. It's gamma in terms of phi. What is the normalizing constant for a gamma? It's gamma of whatever alpha tilde is, divided by beta tilde, raised to the alpha tilde. That's going to be just a function of the beta tilde to the minus alpha tilde. The gamma function depends just on n. That'll go out because you're only doing everything probably up to proportionality. And the inverse normalizing constants of gammas look like t-distributions. We've seen them. So done that on the board, you'll do it again. So it's going to be a t. And you're going to say what the degrees of freedom are. I guess it's not rendering very good. This is going to be n minus 1 is what it's going to be. I typed nu minus 1, that's it. So this is n minus 1 right there. We'll look at the multivariate version of this as well. I might allude to it today. And then I teach you how to sample from this thing using a Monte Carlo sampler. And I ask you to do that. I'm going to explain this step today. So that's what the lecture is going to be about, is this step and how you use it in general. I ask you to plot some histograms and stuff so that you can sample from this distribution explicitly by sampling from this distribution. I'll show you how to do that. Problem 2. Very similar in spirit. You're going to get some other t-distribution at the end of the day. Everything just looks a little bit different. And so this distribution right here will be some t-distribution. Okay? How do I know? This is going to be some normal distribution. That's a normal right here. We're going to integrate over gamma. That gamma, it looks like a precision parameter, but it's not the precision in this context. Some people have other names for it. But again, this is the t representation through a normal mixture model, scale mixture model with a gamma. So you can work through that. We're going to be using this step in a computational exercise in the future. So make sure you know how to do this, where it's all coming from. I ask you to figure out if I integrate over this gamma with parameters alpha and beta, I ask you to tell me what alpha and beta have to be so that this is a T1 distribution. By changing those knobs, I can change the tail behavior. Does anybody know what the answer is? It's going to be a half and a half. So you'll figure that out. You might want to ask yourself a question, what does alpha and beta have to be for this to be T with an arbitrary degree of freedom, nu? It's going to be nu over 2, nu over 2. Work that out. So work through that. You'll have to have done that to come up with the answer half and a half. I asked you to do the exact same sampling scheme in a different context. So you're going to do this iterative sampling that we're going to talk about today in a different context, but you're going to be able to sample from Cauchy distributions. And this should be a fun exercise for you. Don't just sample from the Cauchy once, do it over and over again, and see what Cauchy realizations look like. So they're wild. Crazy. I ask you to compute the min and the max, the range, effectively, from a Cauchy. You'll find out something kind of weird. So every time you repeat this exercise, you're going to come up with wildly different answers. Keep in mind, there's no mean to a t-distribution. So if I asked you to compute x bar or something like that too, you get these crazy answers. It doesn't converge. So all of you should be giving me totally different answers. T's have really heavy tails. So the min and the max are way down in the tails, and those things jump around all over the place. They look like normals, but don't behave like normals. Okay, I asked you to prove something about map estimators. That's the maximum a posteriori, the maximum of posterior. I give you a result that some of you might know. MLEs are invariant to transform. If you'd like proof of that, I guess I could say something about it, but it's almost straightforward. It's in Casella and Berger, and if you've had an inference class, you've seen this before. Maps are not invariant, transformation in general. Just tell you that. There are cases where they can be, and I can tell you which cases those are. This problem asks you to study that. So, is a map invariant transformation? No. I can prove it real quick. So it happens for any distribution. It doesn't have to be a posterior. So let's say I have a normal distribution. It's centered at 0. It has variance 1. Precision 1, standard deviation 1. We're all 1 in that case. What's the map, or the maximum of that distribution? Where does it peak? It's 0. So if I take a transformation of that, let's say I take that normal draw and I square it. So a normal 0, 1 squared, what distribution is that? Chi-squared. So if the maximum was invariant transformation, what that means is I could take 0 squared, and that would be my new maximum. 0 squared is 0. Where's the maximum of the chi-squared distribution? It's the degrees of freedom in this case. It peaks at 1. And Warren just happens to know that because he studies his Wikipedia page, you know? And so he knows properties of his distribution, so that's good. So it happens at 1. 1 is not 0 squared. So that estimator, the peak of the distribution, moves. And it has to do with the Jacobian term. Likelihood functions do not do that. So kind of interesting. Distributions do that, and it has to do with the Jacobian term. So I'll give you just a little heads up. That's what you're thinking about in this problem. Problem 4, this is just a repeat of everything that we've done, worked through these iterated expectations and variances. I can give you a few other problems today that you can work through as well if you'd like some practice. But this just says repeat everything. And then I ask you to solve this integral. And that's the integral that we did the other day before. This integral results from, the integrand results from a flat prior on view. So I did do it in the case where we didn't have the flat prior, so this is a slightly easier variant. But if you can do this problem, you can do the other problem too. They're the same. I think I asked you to prove it's normally distributed. You're going to ask me, how do I prove that without doing the integral? You're going to see that a piece factorizes outside of the integrand. It's e to the minus something quadratic squared. You're done. For me, that's the proof. So you're already finished. But you're going to want to be able to explain this is normally distributed and see if you can explain it to yourself. And if you can't, then do the whole integral by scratch and say, well, there it is. It's normally distributed. But you can see it much sooner than that. So I'm just asking you to recognize that. Problem 5 is another proof that we covered in this class that posteriors are proper if the prior is proper and the MLE exists. Maximum likelihood estimator, so the likelihood peaks somewhere. So if you're trying to figure out how to prove that, it's in a lecture somewhere. It's a one-liner. So I don't think this is a super challenging homework. Just practice doing the stuff that we're doing. I'll give you a challenge on the next one. A little bit more computational. Any questions? Let's just do this basic question right here. Now, I haven't said too much about it, but let's say I have this function right here, f of x, y. Some distribution, x and y are random variables. So when I write something like this, it's always x and y. This f and that f are clearly not the same f's. This is a joint f, and this is the marginal f. So a lot of times, you'll write down x and y or something like that down here, note which f it is, but we're so lazy we never do it. Not the same function, it's just notation. This is the margin on x. And we're playing around with problems like this. In Bayes land, everything's a distribution. That distribution has properties, we need to understand that, but basically if you think you're working with the right distributions, you've got the right priors, you're inducing properties that you like in your posterior, you're able to do inference. Basically, everything is just probability. So at the end of the day, and that's kind of the nice thing about Bayesians, is that everything's on a probabilistic scale, so if you remember your probability class, you're in good shape. You can do Bayes. Let's say, let me give you a little bit. Say you can sample jointly. So I can give you xi, yi pairs from the joint distribution, fx, y. So let's say I'm able to give you those joint samples. So if it's a normal distribution, some sort of an ellipsoid, and I'm able to grab points under that elliptical bell-shaped thing with frequency proportional to the height of the density. That's what it is to sample. So say I'm able to sample something jointly, how would I recover the margin? Say I've got a whole bunch of these pairs right here. I goes from 1 to some large number, I'll call it k. And I end up getting all of these pairs. x1, y1, x2, y2, x3, y3, dot, 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 x cap k, y cap k. I've got all of these pairs. And somebody says, no, I don't want the joint relationship between x and y. I don't even care about y. I want you to go redo this whole thing, do this integral, figure out that, and then sample from this thing. What would you tell them? So say you're able to sample jointly, and then I come in and I say, I don't want that. I want the margin. So what I want you to do is I want you to integrate, do this by hand, and then build a sampler for that. What would you say? I would say no. Yeah, please.
Well, we have the samples, like side ladder, then we just ignore the y's.
Just ignore the y's. Yeah, exactly. So these are joint samples from this. These right here are just samples from x. So you already have them. So if you just ignore them, that's doing the integral. So Monte Carlo integration is the easiest thing in the world if you're trying to marginalize something out. So these come from x. Integral fxy dy. Integrate over all of y. These right here come from the other integral where I marginalize out x. So that's marginalization in a nutshell. If you've got joint samples, you've got the marginal samples. How would you get conditional samples? Say I wanted conditional samples from like this. X given y is equal to 3. Yeah, maybe divide by the marginal, so, but what would I do with it? How would I take these samples and turn them into that? So again, I don't want to do this all analytically. I don't want to build those distributions per se. Yeah, plug in y is equal to 3. So take this thing, shove y is equal to 3 in there, and then always sample from this where it is conditional on y is equal to 3. Just plug that thing in. You could look over all your joint samples, and for the ones where y is equal to 3, you could collect all of those x's, and those would be the conditionals. You'd have to have a pretty good imagination to do that, because if y was continuous, you'd never see it being equal to 3. Hardly ever. So what you would do is you would just pin down that and then sample from this. If you had an infinite collection of samples and this was a continuous universe and your computer gave you that stuff, then you'd look for the ones where y is equal to 3, and it would be the slice through that joint distribution where y is equal to 3. So Monte Carlo is a good, it's helpful, especially if I'm trying to understand marginal relationships or report things marginally. I can work with the joint distribution and recover basically whatever I want. Makes life easy. Say I have these samples right here. Let's just do another one. How could, so another question, we get samples from, let's do this. Let's make this kind of hard. E to the minus sine arctan x. So this is just some weird transformation. So I'll just call this tau x. This is a transform. I picked this function for no, I've never seen this in reality. It's just some function. It's supposed to look crazy. So you might think, well, I do a transformation of variables. If I know what this is, then I can invert this thing. Ooh, hard to do. You're going to have a hard time inverting that function, right? It has all these asymptotes all over it. Arctan is kind of weird. And then this is making it look even weirder. This is pushing the tails down, doing something weird. So you'd have a hard time doing this analytically. So what you'd have to do is invert, solve for x, call this something, we can call it tau if you'd like. Solve for x in terms of tau, take the derivative of that thing. That would be your Jacobian absolute value, and plug that thing in to this equation right here. Hard calculation, you won't be able to do it. So if I wanted to sample from this, I could learn all about this transform distribution. How would I do it? How would I get samples from this if I'm able to sample from that? Do you have to do any math? No. Somebody help me. What would I do? Ignore the y's again. So I've already got the marginal relationship right here. And you could say, well, no, I need to do, you don't have to do any math. Then what do I do? Yeah, just evaluate. It's that easy. You just plug them all in. Boom. These right here are samples from tau's distribution. So you can just take them and you just plug them right in. Easiest thing in the world, transforming random samples is really easy. You just plug them into your transform function and that's what it is. That kind of makes things easy. So if I have posterior on one scale and I'm able to sample from it, and somebody says, I want it on this other transform scale because that's the way I think about it, I just take those samples and transform them directly, draw a histogram of that thing, and that's the distribution of your transform. That's all very nice. Where does the Jacobian go? Say that x and y were both continuous. When I worked in continuums before, I needed the Jacobian, right? So it seems like in discrete land, I was able to just plug things in. Do I have to worry about stretching the space or anything like that here? You do not. Remember, samples are discrete. So they are a discrete representation. You don't need any Jacobian. You're not working in a continuous space anymore. Everything is discrete to you, even if the underlying random variable lives in a continuous space. So the whole point is, if you're able to joint sample from something, you can have anything you want. So let's say I wanted this. Just to drive the point home a little bit more. Say we want expectation of tau x. So this crazy function right here. So I want a transformation of x. X is this thing right here. So it'd be pretty, like if somebody asked for this in general, I might think this is a hard problem. That you want me to integrate this, I'm not sure, I can only do a few integrals. You know, a lot of things you can't write down explicitly. You can always differentiate everything, but we can't integrate everything. We can't go the other direction. In your calculus class, you probably learned about 7 techniques. And there's more, but a lot of things don't have analytical forms. You can't express them. A Gaussian distribution is a good example of that. So how do I get the expectation? Say I'm able to sample from the joint. I can't probably compute it analytically, but I could take these samples right here. I'll call my tau i's, are equal to e to the minus say minus sine inverse tan x. And I plug this in right here. So these are samples from this distribution. How did I get them? I just collected my joint samples. I threw away the y's. And I get all of these. So I can approximate that very easily. So I'm going to just say this is 1 over k. That's the number of samples we have. Sum, I'll say I goes from 1 to tau k, tau I. So I'm just using the arithmetic mean that converges to this. How does it converge? Well, there's a central limit theorem playing a role as well. So as k is big, I get very, very close to that. Law of large numbers says this converges. How would I end up coming up with maybe the variance of tau? Same thing, I just take my samples and I treat it all very empirically. So I'll say this isn't equal, this is approximately, and as k goes to infinity, it is equal. Something you'll never have. Yeah, it's a concept. This is just going to be something like this. I'll say tau I minus tau bar. This thing right here is tau bar. Squared. I goes from 1 to n, 1 to k. What do I divide by? I'm just curious what you guys say. It definitely matters. There's some bad choices. But you might have 2 or 3 contenders where it doesn't really matter. So, what's your choice? Okay. Sometimes you might do -1 if you wanted this thing to be unbiased. Peter likes minimal MSE, is what he just told me. So this minimizes the mean squared error. This is a more stable estimator. It's actually closer than the k-1 one. So the beauty of this, what I really like about this, again, all those asymptotic properties you learn in inference class are still true, but in Monte Carlo land, I have control over this. We get to crank that up. So I don't love asymptotia when I'm doing my inference, where I say, well, what should n be, and I'm going to control the power. I'm not that kind of statistician. So I do things conditionally. I don't like that asymptotically, this is whatever distribution. I like to come up with a conditional distribution. Good example of why I like the Bayesian thing is that theta binomial problem, where you're coming up with coverage intervals. The Bayesian thing works a little bit better. There's other ways you can explain it. You don't have to be a Bayesian to do that per se, but it does give you a framework for doing it. Penalizing your likelihood effectively. K's going to be so big, it's not going to be one of these fringe cases where it's like, well, K's only 20. You know, and you're doing Monte Carlo, it's going to be like 10,000, 100,000, a million. So you're just going to run it on your computer for a long time, and you're going to get better and better estimates. You're going to crank K up so that this thing isn't jumping all over the place. That thing's not jumping all over the place. So if I can sample jointly from something, I can learn everything I need to do in kind of a math-free spirit. Turn everything into a computational problem. You don't need to solve things analytically. If you can, you should. But if you can't, which is a lot of cases, then you do Monte Carlo. Let's come back to posterior predictive distributions. See if we can figure this out. Our framework looks like this. So the posterior predictive looks like this. Integral, whatever my original distribution is, I'll say theta are my parameters. I don't know them. I built a posterior form that I integrate over the uncertainty expressed in my posterior distribution. all of theta. So that's my posterior predictive distribution. Say you know how to sample these two things, posterior K. And you know how to sample from the original sampling distribution. I can grab x tildes, those are my future. I can sample from this distribution. So if I knew theta, I can sample from f. Plug it in, I'm able to sample. I also know how to sample from my posterior distribution. So some easy cases that we know about already are like the normal, where theta is representing the mean. I know how to sample from a normal distribution. The original sampling distribution is normal, and the posterior is normal. If the variance was also unknown, then I might make this joint normal gamma-looking thing, where I operate on a precision scale. And maybe I could sample from that as well. So you know how to sample from both of these things. You can do it as many times as you'd like. So how do you sample from this? I'll give you a hint. It's not hard. Do you know how to sample from the joint distribution of this? If you know how to do these two steps? How do you sample from the joint? Let's just ask this first. Say x tilde and theta given x. So this is a joint of your future sample and what you think theta is. But you only know how to do these two samples. Pretty easy, right? Yes, please.
Well, I mean, if they're independent, you can just sample.
Yeah, but they're not independent, right? Because this one's conditional on theta, so there's a dependency. So you're right. If they were independent, you'd just sample from both of them. Pair them up in a column. You could even shuffle the order of both columns if they were independent. But this problem is not independent, because there's a dependence between x tilde. How do you extend to the non-independent case? What do I do with the theta in between? Plug it in. Yeah, you sample hierarchically. So what I would do is I'd first take theta k, sample it from my posterior, and then I would sample x tilde from that distribution, but I would take this theta k and I would plug it in. These samples are joint samples. The result is x tilde k, theta k, come from this joint distribution. I'll say x tilde theta given x. So they come from that joint model, conditional on cap x, because that conditioning was right here. So that's all you do. So if I can get joint samples, then I can have just my posterior predictive sample. So the answer to this is this scheme right here. If I just wanted x tilde, now I just focus on these. So these right here come from star. Goal. So if you can sample from the posterior, generate that sample, you plug it into the sampling distribution, and that uncertainty is being propagated into the samples of x tilde. So we're shaking theta along the way. And it's creating that extra uncertainty And ultimately, it's solving this integral. So, boom. Once you can do that, life is easy. So later on, I'll teach you how to sample from this, even if you don't have a button on your computer for doing that. And I'll teach you general schemes for sampling from these things. But this is kind of a Bayesian world, at least the modern Bayesian. In the 60s, we used to tell you about the likelihood principle. We'd argue with you about what the evidence of the p-value was, what was it saying about the null hypothesis, and that's not evidence, and we argue with each other and say there's a better way to do it, and everybody fought with each other. This is the thing that's converted probably most people. Oh, I can just run Monte Carlo and get these samples, and I can transform and get anything on any scale. And I change this hard integration problem, hard calculus problem, into a computational problem. And so Bayesians got very interested in how do you sample from distributions that look really funny. So, and that's the land of Markov chain Monte Carlo or important sampling, and I'll teach you what those things are. So later on, I'm going to say you know how to sample from anything out there. How effectively, how fast you can do it, that's of course one of the big computational concerns. So hopefully I've expressed to you guys that sampling from things is what you need to be able to do, and then you can approximate anything you want. So everything you want is basically going to be expressed in terms of an integral. And so if you can sample from things, you can compute all these integrals. That's all very nice. The homework drags you through this and makes you do all this sampling. So hopefully it becomes clear once you sit down and you do it. And I'm going to keep having you practice that. I think I should tell you some more general results before we move on. I'll probably tell you a little bit about intervals next time just to fill in some gaps. Not a super mathematical conversation. Tell you how Bayesians construct intervals. I'll tell you some of the computational things that we do to compute intervals, but I've taught you at least one interval. And you chop off the tables. There's other intervals though. Let's come back and do that next time, but I think I'll just ask you some questions about posterior predictive distributions. So here's just a few examples. Let's say x's come from a, let's do a binomial distribution. Just distributions we've touched already. So let's just say you see a whole bunch of samples here from this. Xi's, I goes from 1 to n. Oops, 1 to n, let's call it m, because I already used n. Equivalently, I've got an m times n samples from a coin flip, from a vertex. They're the same. A lot of times you guys will ask me, do I get multiple samples from this? Usually I say, if it is there already, it's the same problem, so I don't really care if you see multiple samples. Okay, so let's say P, how would I form this? I'd probably pick a theta. So I need to talk about my priors. I need to pick these for you. In a default case, I usually pick these to be a half and a half. I'll give you more good reasons for that later on. So far, you've just seen it in your homework that seemed to work. That U-shaped thing kind of makes sense, but we haven't done anything mathematical to explain that. We will. What's x tilde given x? This distribution. So that's the posterior predictive. Does anybody know what distribution this is? You can just kind of imagine what it looks like. So this thing right here is just going to be equal to integral, I'll say it's proportional to, just so we can kind of get a handle for what it looks like. This is going to be p to the sum of my xi's, 1 minus p to the n minus sum of the xi's, m. top. I guess I should product this up. This is going to be I goes from 1 to m. This is why I always kind of hate this. This will just change to k, just like this, xi, n minus xi. Integral p to the alpha minus 1, 1 minus p to the beta minus 1, pp. I integrate between 0 and 1. This product ends right here. Could you figure out what this is? What distribution does this look like? It's a bunch of gamma functions, isn't it? This big beta function inverted. This right here is a beta function. You can figure out what it is. This is actually called a beta binomial distribution. So it does have a name. It tells you exactly how it's formed. So you can write down the functional form. This is a beta binomial. I could just keep this going and just say this is going to be p to the sum xi's. I goes from 1 to n, 1 minus p, and this is going to be plus alpha minus 1. So I'll combine this with my prior. 1 minus p. This is going to be m times n minus sum. I goes from 1 to m xi's plus beta minus 1 p. Remind everything's up to proportionality. So what does this thing look like? This looks like a beta function. If you don't like those, you can represent it as a bunch of gamma functions. It doesn't really help you any. And it's going to have a few parameters in here. I'll call it alpha tilde, beta tilde. I'll show you where those are. This one's alpha tilde. Oops. This one's beta tilde. So the distribution looks like, and this will be inverted. Look it upside down. So the distribution looks like a beta function. It has some shape to it. Hard distribution to understand. You don't have any familiarity with it. But it's some distribution and it produces some counts of things. So these are those posterior predictive counts that are going to live between 0 and n. So you could normalize this. And if I asked you to find the expectation of this distribution, it would be a hard task. But if you knew the iterative forms, you wouldn't have to do too much calculus. You could say the expectation of this thing is going to be equal to the expectation of x tilde given p and x. And I'll iterate my expectation. Conditional on x. What is this thing? This is the expectation is p given x. This is my posterior expectation right here. What is this? This is going to be all the sums of the xi's right here divided by n. And that's what it turns out to be. You could work that out. You might know what this expectation is. Oh, sorry, this is not it. Asymptotically, it's it. This is going to be alpha tilde over alpha tilde plus beta. Asymptotically, it's delete. It has these little alphas in here. If I asked you the variance, you'd use the variance form to come up with that. So you would report this is whatever this function is. beta binomial distribution and the expectation of the variance are those. Let's do another one. We can do this over and over again, and this is what I'd like you guys to do. So when you see me work on a problem with some distributions, change the distributional assumptions and see if you can work it out. This one's always good. Let's say, a new example. Let's say x's are coming from a Poisson distribution. Maybe we should pick up with this next time, because you guys might not know very much about Poissons. I'll say i's go from 1 to 10. You get to see them, and you want to learn x tilde given x. What are we integrating out of the problem? It's the lambda in a Poisson. I'll write down what a Poisson looks like. This will help you to answer my first question about this. But fx given lambda e to the minus lambda. Lambda can be x over x factorial. Lambda is positive. And the x's are counting numbers. So they go off to infinity. So this is 0, 1, 2, 3, all the way out. So Poissons are your fundamental counting distribution. Maybe I should say a few things about Poissons instead of just leaving it as a general distribution, but I think I'll come in next time and say some stuff. Let me just ask a quick question about this. Which prior would you use on lambda? Yeah. So instantaneously you recognize, oh, if I do a product over this thing, it looks like it's a gamma in terms of lambda. And so you know what happens. So gamma is your conjugate choice. If I told you to pick the hyperparameters in that gamma, what would you pick? Let me ask a question. What is lambda? What kind of parameter is that? It's a mean, right? It's also a variance. Right? So Poissons are kind of funny distributions. The mean and the variance are both lambda. Lambda is acting as a scale parameter in that sense. So what would you pick the distribution on lambda to be if I said it that way? Maybe the gamma 0, 0. That would give me 1 over lambda in proper prior. Same argument as before. So let's say I want to figure out this. Right here. Integral this is my posterior distribution, and I'm going to integrate over this from 0 to infinity. What distribution do you think this has? I'm going to put a tilde here to let it represent the future. X tilde given x is this thing. This will be a gamma if everything is conjugate. This will be a Poisson. This will be my posterior predictive. Which distribution do you think that is? Any guesses? At least somebody throw out one guess and I'll let you go. I was hoping you would do something like that. Let me ask the first question I always ask to do a sanity check. Where do t's live? They're continuums, right? Living between negative and infinity and infinity. I hope that's not a t. Because it counts. So, take one. Why don't you guys come back next time? See if you can answer this question. And see if you know of any other counting distributions. I think it'll be a distribution. Stephen's mad that I won't give him the answer. It's a negative binomial. And they're very interesting. And they don't have means that are equal to its variances. We'll come back. We'll look at this next time, and then I'll tell you something about intervals. And then we'll get into something a little bit fancy. I think that's it. Thank you guys. Wednesday review.
Wait, 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 not
Sorry.
straightforward.